we should all experience in the coming years about this new window that will be open to observe the universe, the gravitational wave window. Undreamt by Einstein, because although Einstein was the first to work out solution of his equations, the wave-like solutions of his equations, he, for the rest of the time, tried disproving the existence of gravitational waves. He did not believe their reality because of many complexities that arise in a theory like general relativity, which has many gauge degrees of freedom. And so he thought these were artifacts of his theory, and there was no way to produce them. So he didn't quite believe in them. So even Einstein could not have imagined the state in which we are, where there is more than $1 billion spent in building gravitational wave detectors throughout the world. So that's the situation. But let's start with a very simple picture of what gravitational waves are. According to Newton, space is very rigid. Things take place in space-time, but otherwise time is absolute and space is rigid, nothing changes, and you have a very rigid space-time. That changes in Einstein's theory of gravity, where space becomes part of the actors, and space-time is very fluid. It's like a jelly, and it can be moved, it can be stretched, it can be squeezed. So this kind of very dynamic space-time is what we call gravitational waves. The wave-like part of it, the so-called technically non-stationary solutions of Einstein's equations, is what we call gravitational waves. There are many students here, and you would have seen that the fundamental aspect of gravitational waves is to stretch and squeeze space-time as depicted in this very nice but simple photo or sketch of how the space-time gets kind of deformed in the presence of gravitational waves. But in order to stretch and squeeze space-time, you need to expend some energy, and it is not very easy to do so. So if you look at space-time rigidity, it turns out to be not so small. We will look into exactly how large a force you need to apply to cause any appreciable change. But really, the point is that we cannot really produce appreciable amounts of gravitational waves in the laboratory, and we rely on very catastrophic events in the universe, and the examples of which include colliding black holes, colliding neutron stars, and the Big Bang itself. So when we talk about detecting gravitational waves, we are talking about detecting extreme events in the space-time. And because gravitational waves interact so weakly with the rest of the matter, it's going to be very difficult to detect them, and only these examples that we have here are the ones we have any hope of detecting at all. But how rigid is the space-time really? Is it really so rigid that we can't change its structure easily? The answer comes from Einstein's equations themselves. If you look at Einstein's equations, there is a coupling constant. I'm sorry for the faintness of the fonts there. That is the Einstein tensor, that's the energy momentum tensor. This quantity 8 pi g by c to the power of 4, the inverse of it rather, has dimensions of force. Very easy to work out. And it is very large force. So in human units, I would like to call it a geometric force. C to the power of 4 by g has a magnitude of 10 to the 44 newtons. It is extremely large compared to anything that we have experienced so far. So can this really occur in nature at all? What are the situations under which such a large force can occur? Under what circumstances can such a force be felt by bodies? So let's take an example which will recur throughout the talk of a body orbiting about another massive body. In this case, we learn that it's a simple expression, m v square by r. M is the mass of the body. V is its velocity, and r is the distance to the gravitating body. That's the force that it experiences. But from Kepler's law, we know that m by r is nothing but v square upon g. So I'm going to substitute for that m by r and rewrite the force as v to the power of 4 by g. That's all that is going to occur. Characteristic velocity, orbital velocity in the system divided by Newton's constant. I'm going to rewrite that as c to the power of 4 by g into v by c to the power of 4. That's a dimensionless number, and you have the gravitational force sitting in front of it. So for any system in an orbiting body, this is raised to the power of 4. Let's take the case of Earth. It is 10 to the minus 6 of the speed of light. So the force that is felt is 10 to the minus 24 smaller. So when can we really expect these forces to be large enough to be close to the geometric force? The answer is only when v goes to c, and that can happen close to black holes and neutron stars. And these are the systems that are going to experience that kind of force, and therefore they will in turn exert that force on the space-time region. So this is when you can really experience it. But it is not any damn black holes or neutron stars when v goes to c, but only when they are very close to each other. And it doesn't matter what their masses are. It can be very tiny, such as, I don't know, 10 to the minus 5 grams, or it could be very large, 10 to the 10 solar masses. No matter what, the speed of light, the speed of the bodies reaches around the speed of light, never larger than that, when the two objects are close to each other, which means merger. So we are talking about merging neutron stars and black holes as sources of gravitational waves. That's the only hope of really stretching and squeezing space-time, is when we have neutron stars and black holes. But what has this got to do with the gravitational wave amplitudes themselves? You would have learned in the school that the strain produced by a self-gravitating mass, it could be a neutron star, or a white dwarf, or a pair of black holes, or supernova, it doesn't matter. The rough order of magnitude estimate of amplitude of gravitational waves is a product of internal gravitational wave energy, that's the internal energy, gm by c square r, multiplied by external gravitational potential. Okay, this is the external gravitational potential because that's the distance to the source, and that m is the mass of the source. So how long, I mean, we can now rewrite this expression in terms of the gravitational force all over again. It's a simple rearrangement of this, and again you use Kepler's laws, and you come to the point of expressing the amplitude of gravitational waves as v to the power of 4 by g, that has dimensions of force, divided by gf, multiplied by this ratio r upon d, which is the distance to the size of the body, or the size of the source of gravitational waves, divided by the distance to the object. And it turns out, because waves can be defined only in the wave zone, it is always going to be true that r is going to be much smaller than d, or d has to be much larger than r. So this factor is going to be less than 1, and this factor is also going to be less than 1, and only when you have these objects in the form of black holes and neutron stars can you expect this to be taking the maximum value, and in which case it will be of order 1. So the amplitude of gravitational waves, again from this very simple illustration, can be shown to be take the largest value when you have black holes and neutron stars. Really in no other circumstance, especially when the two are colliding, can you expect them to be really large. But this is not the only way to produce gravitational waves of detectable amplitudes. You could have a situation where the wave lasts for very long time and you integrate. That's another way to do it. But if you want to have transient gravitational waves of appreciable amplitude, we are basically talking about neutron stars and black holes, and maybe the processes in the Big Bang itself. So let's now look at the sources of gravitational waves as a summary. I will talk about some of them as we go along. So the first in my list is really those binaries, which consist of neutron stars and black holes, sometimes white dwarfs too, basically compact objects in the universe, and that's why, and we call compact object coalescences as compact binary coalescences. Gravitational collapse in supernova can produce situations where the compactness, which is the mass of the system divided by its size, gm by rc square, can be very close to 1, and that's the reason why supernova are interesting. Low mass X-ray binaries, pulsar glitches, and magnetars are other examples involving neutron stars which can produce copious amounts of gravitational waves. The other interesting example is simply an isolated neutron star spinning rapidly in the frequency band of your detector. It could be white dwarfs or neutron stars with proper periods, proper frequencies of their spin, which could produce copious gravitational waves. Stochastic backgrounds, and both of primordial and astrophysical origin, could in principle be sources of gravitational waves, but we will see what is the potential to detect them later on. So I'm going to take each one of these and tell you something about their property, and then see what kind of detection rates we can expect for them. So let's start with binary black holes. These are the simplest systems you can think of. Fortunately, it's also very easy to, I wouldn't say easy, it's possible to model them. You can produce gravitational waveforms, both using approximation methods, but also using numerical methods which are exact. The waveform is pretty simple in the sense that for a long time, the system really does nothing other than having a slowly evolving frequency. We call it adiabatic in spiral. The amplitude keeps on ramping up. The frequency keeps on ramping up until a point when the two black holes are almost touching. We call that the merger phase, where one expected in the past very strong nonlinear dynamics to take over, and hell can break loose and you can produce all sorts of waveforms. But it turns out that, as predicted by one of the analytical models, it's a very simple continuation of the in spiral, natural transition to the merger phase, and then that is followed by a highly deformed black hole which produces the radiation of a ringing black hole or a quasi-normal modes. So that is the expected picture, and the way to deal with it is there are many pronged approaches. So let's look at how this problem is solved. On the y-axis, I have what is called, essentially the size of the system. It's RC square upon Gm. It's the inverse of the compactness. The higher up you go, the less compact it is. Towards 0, you have more compact objects. On the x-axis are the mass ratio of the system, m1 upon m2. Here you have equal masses, and you have very highly unequal masses at the right. So first of all, the ones that were really used for a long time ago are the so-called post-Newtonian approximation or post-Newtonian theory. You may have learnt about this in the school, and it was pioneered by Einstein himself. He used post-Newtonian theory to calculate even the precision of perihelion of Mercury, and it has been very successfully used, but it does not produce any unique waveform, and there are many approximants, and they are called by names, funny names like Taylor T1, Taylor T2, Taylor T3, but there are also frequency approximants like Taylor F2 and so on, and there are many of them, and we have no clue, or we did not have any clue which of them was correct before numerical relativity came and told us, hey guys, this is the exact solution. And then one could compare those Taylor models with the numerical relativity models and get a more precise expressions. Here the problem is of two kinds. One is the binary neutron star problem, the other is binary black hole problem, and now there is an industry of people working on solving these problems because it requires different expertise, different physics to solve the binary black hole problem, and it requires different physics to work out the binary neutron star problem. On top of all these things is the perturbation theory, which was pioneered in calculating what a deformed black hole does by Vishveshwara, and then followed by many people. And this is another industry because these are the kind of sources with very high mass ratios and potentially very close orbits can be seen in certain detectors, and therefore there is a whole industry here too trying to solve this problem. What on top of all this is the so-called effective one-body problem, which tries to unify the different approaches into a single analytical treatment of the problem, and that is called the effective one-body model, started off by Bonanno, who was lecturing here last week, along with Damore, Nagar, and again quite a large number of people work on it. So today we have a very good handle on the binary black hole problem, but not so very well on binary neutron star and neutron star black hole problem. We think that in principle binary black hole problem is solved. It's a problem of getting hold of the parameter space a little bit. The corner cases where you can have extreme spins or the spins are not oriented along the orbit could be very interesting, and therefore they may be the ones that have unique physics that will help us understand the two-body problem better. And so there are some problems left out, but as far as binaries with matter is concerned, we have a long, long way to go. And so how does this numerical relativity waveforms look like? I'll give you one example. There will be other talks which will tell you. Let me show you this iconic movie of a black hole orbiting another black hole. What is shown in this simulation is the waveform, how it develops as a function of the distance between the two bodies. This is a very simple movie produced by a numerical relativity simulation. The color shows you the depth of curvature and the color and the hue, and these arrows tell you the direction of the velocity vector. So here you go. I mean, the two black holes are going around each other. As they go around each other, slowly the amplitude and frequency ramps up, and then we will jump the movie somewhere here all the way to close to that, and you will see a highly deformed black hole, and that deformed black hole contains a lot of energy which will be converted into gravitational waves. So the two black holes come and they collide, and initially it's highly deformed, and that deformation, that is the point at which you reach the maximum amplitude of gravitational waves and you have a ringing black hole. This is the iconic picture that or simulation. There will be many examples, and I took one of the old ones here to just show you. This is something that people have been doing for almost a decade now. Now we talked about binary black holes. What is the relevant parameter space? The relevant parameter space is really the mass of the binary system, the total mass, and the frequency. And the different frequency regions are targeted by different detectors. Detectors that are built on ground, some of which we will hear about, target basically the audio frequency, something like 1 hertz to about 10 kilohertz. The frequency slightly lower, from a few times 10 to the -6 hertz, let's call them 20 microhertz or so, up to about 1 hertz is targeted by space detectors like laser interferometer space antenna, and very low frequencies, something like nanohertz, is targeted by pulsar timing arrays. So if you see a source in any of this region, you can see which detector is going to observe it. One of the most fundamental frequencies for these systems is the so-called loss stable orbit. I said the most interesting sources are those that touch each other, and they are in orbit, and they don't have any more orbit after they come to a certain point, and that's called the loss stable orbit frequency. And it is simply 1 upon the mass. Okay, there's a simple expression, 1 by 6 to the 3 by 2 pi times m in dimensionless units, sorry, c equal to g equal to 1 units. And that would give you this dependence, 1 upon m, and because it's a log-log scale, it looks like a linear thing. But those are not the only relevant frequencies when binary black holes merge. They produce this ring-down frequency and the so-called dominant frequencies. You know, it produces many, it's a spectrum of frequency, you know, spectrum of radiation, and the most dominant one is this line here. And there are higher order modes. Numerical relativity predicts that there are higher order modes. That is called the 3 QNM frequency. But the amplitude in this higher order modes is not going to be very large. So we do not expect appreciable amounts of radiation after something like the 4 quasi-normal mode frequency, at least not in the ground-based detectors, I would say. In space-based detectors, occasionally you may have an event which produces higher order modes too. So really we don't expect any radiation, and if you see something in that region, that means there is either something wrong with general relativity. These are not black holes. Maybe these are more compact objects than even black holes. They could be naked singularities and all the rest of it. So we will run to produce theories which will, you know, produce radiation in that. At the moment, nobody cares about that region. There is no expected radiation. On top of this, let me also show you a line that gives you just 1 minute to merge. Any object that is starting, let's say a 100 solar mass object starting at a frequency that you can read off here, will last just 1 minute before merger. So that means that binary neutron stars at the leftmost end here are definitely going to merge as observed by ground-based detectors. It doesn't matter whether you take even 1 hertz. For instance, this one here is 1 day to merge. This is 3 years to merge. So all the sources that we are going to see in ground-based detectors, right, they're all going to merge. So that's why we talk about merging binary black holes. Oh my goodness, I'm not even 1/10 of my thing. Okay. All right, and then you have you know, more massive black holes in LISA and so on. So let me go to accelerate. But not all the systems that we are going to observe will merge. They are systems which simply stay in one frequency in things like pulsar timing arrays or in LISA. They don't chirp up at all. So there are other lines too. This line represents how much time it takes for the object to chirp up, and that's about 1 day. It will chirp up in 1 day. But there are other lines which will be above this, and it will take only 1 minute to chirp. So everything that we observe in ground-based detectors are definitely going to chirp. And so also in the case of LISA. But there are other lines that I have shown here. It takes 1 year to chirp, and this takes 30 years to chirp. That means there is no change in frequency even after 30 years. It sits in one point. And unfortunately, you can't learn a lot about a system that doesn't chirp up. You can't measure the parameters. You can't tell how far it is, and so on. So to be able to be able to do astronomy, we really need chirping binaries. And this region here is change in frequencies less than 1 nanohertz. Those that lie in this, we have limited understanding what we can do with that. But there are certain things that are being, certain things that are being explored to change that situation for pulsar timing arrays. If anybody asks a question, I might touch upon that. Okay, the radiation, goes up. Let me just skip that. I'm going to skip that too, but let me just come to this one. The binary neutron stars are the next set of sources that we are interested in. These are fortunately the sources that we know exist in nature. There is the so-called Hulse-Taylor binary pulsar, which for many years, not anymore, was one of the most relativistic systems that we observe. What is plotted here is the cumulative periastron time, which will be just flat. That means the binary comes after a certain period, exactly at the same period in Newtonian gravity, time after time, orbit after orbit. Whereas in Newton's gravity, it will come slightly faster every time. So you subtract off the Newtonian one, what you get is this curve here. The curve is really the prediction of general relativity based on the Keplerian parameters that are measured, and the dots are the ones that are observed, and the two agree with each other to less than 0.1%. One of the most spectacular conformations of generativity. The problem here is the observations of them in gravitational window should constrain models of formation and evolution of compact binaries. It should be possible to even measure the equation of state. For that, we need a very bright event. But the rates here are very uncertain. In the binary black hole case, I didn't talk about the rates at all. But in advanced detectors, we could see between 0.5 and 400 per year, whereas in future detectors, this rate might go up significantly, like Einstein telescope, which I may not have time to deal with. This is an argument which I won't go through in the interest of time, which tells you what is the rate you can expect based on the observed gamma ray burst population, short gamma ray burst population. It's actually a pretty interesting calculation, and it tells you that the detection rate could be anywhere between a few to about 50 per year in the LIGO-Virgo detectors. So let me now just show you some graphs that depict to you how far we can see with these and what we can do with them. So this plots the network efficiency, the efficiency of the network of gravitational wave detectors like LIGO-Virgo as a function of the distance. So these initial advanced detectors that the advanced detectors that we are building have 50% efficiency, and that varies. The distance up to which it has 50% efficiency varies depending on what network we use. If you use only 2 detectors, it's something like 200 megaparsec. If you use all the 5 detectors in the network, it's about 300 megaparsec. What is interesting here is not about the distance, the so-called horizon distance, the maximum distance up to which we can see, does not change with the increase in the number of detectors, but what changes is the completeness. You make your catalog more and more complete as you add more and more detectors, because you get more straight line here, and that's what is interesting. So that's for binary neutron stars. Binary black holes can be seen at cosmological distances, 1 gigaparsec or larger, and that's for the efficiency. But for the expected linear rate density, which is the number of events per year per megaparsec, what you're saying, that linear rate density for neutron star, it turns out that we should expect, based on this estimation, 100 mega year per mega year per Milky Way equivalent galaxy. That's the assumption that is made in deriving these rates. The number of neutron star coalescences is 100 per million year per mega year. So in fact, the more interesting one might be this plot here, which shows you event rate as a function of distance. Where are our detections coming from? They are coming from about 400, 500 megaparsec for binary neutron stars, about 1 gigaparsec for neutron star black holes, and at cosmological distances for binary black holes. So that's the summary of where we can see. The binary neutron stars are very interesting from a point of view of telling us about the supranuclear equation of state. And this shows you that unlike binary black holes, which have very simple waveforms, especially the so-called post-merger signal, that is long in spiral that is followed by the post-merger signal, can be pretty complicated. So that's what is plotted here. In this particular case, as you go from top to bottom, the equation becomes stiffer and stiffer, and as you go from left to right, the total mass of the system increases. So these are lighter systems and softer equations of state, and these are heavier systems with stiffer equation of state. As you can see, the post-merger signal is high frequency in this case and low frequency there, and which means that we will be able to tell by gravitational wave observations what the equation of state is for these systems. I will skip that spectrum. So in addition to these binary systems, one of the most sought after and also very big physics prize is really core collapse supernovae. The reason is we all know that we come from star stuff, and supernovae play an extremely important role in that whole phenomenon of producing us. But the problem here is we cannot collapse and then produce an explosion. And that's been the problem for many, many years. And it's an outstanding problem. We know how much of energy reservoir is there. And the details of the physical process here is not known. And as a result, we really don't know what the amplitude of gravitational waves we can expect, namely how much of energy in the star will be converted to gravitational waves. The estimates are between 10 to the minus 6 solar mass to 10 to the minus 8 solar mass, but we really have no clue. There are accretion-induced collapse as well, and the problem here is similar. The explosion could be very weak, and it could be subluminous, and therefore we may not really see them in optical, and these could be what are called the silent supernova, and the only way of observing them, especially at great distances, might be via gravitational waves. The holy grail in our field is really observing the birth of the universe in the form of stochastic background, in which what is shown here is the time moves up from top to bottom, and waves that are produced on Planck scale are traveling to us unscathed, and we should be able to observe them if they are of sufficiently large amplitude. At the moment, there is really no mechanism of producing large enough amplitudes that will survive up to the present day at observable amplitudes. So it may not be possible to observe them except probably using pulsar timing arrays, which will reach the level of 10 to the minus 15 when you have the square kilometer array. I'll skip that. And I have, Matt, I think I have about 10 minutes? Yeah. Okay. Okay, all right. Oh, is that right? Are we not supposed to be 45 plus 15? Yeah, we started 5 minutes late. Okay, all right. Okay, I'm going to skip Lisa. It's not very interesting. You can see how much time I've spent, and there are so many of them, okay? So I could have talked about them, but I probably will not, because otherwise I will not finish. So I want to really talk about this, because this is coming pretty soon to one of your theaters. Advanced detector network. We have 5 of them planned, 3 already under construction and being finished, and 2 of them either under construction already in the case of Kaga, are waiting for money in the case of LIGO India. So we have those detectors. So we will be making detection soon. In addition to that, we're already planning to build the next generation of detectors. Einstein telescope might well look like this: underground, 10-kilometer tunnels, triangular shape, 2 detectors in each of the V's of the triangle, right? And totally 6 detectors in the array. That's one of the dreams. And that probably will cost about $1 billion. But who cares about money? You can dream. But these detector networks are very interesting, because the moment you build about 3, you cover the entire sky, probably 70% of the time. But the moment you have about 5 of those detectors, what is plotted here, I didn't explain, is the sensitivity in different directions. And that is kind of anisotropic when you have 3 detectors. With 1 detector, which is the quadrupole pattern. With about 5 detectors, you have roughly uniform sensitivity over the entire sky. Maybe 50% of the time, you observe the entire sky. So it's a all-sky survey detector. But the problem is, we can't tell where the gravitational waves are coming from with a single detector. With a network, we can. And all the pointing is done in software. So we can integrate and build SNR by coherently tracking signals in phase, which means we can have long signals, short signals, all of them buried in the same data. So this is, from a data analysis point of view, a very hard problem, and a problem that can attract tons of postgraduates each year, but we have to have some signals first before we can attract more people. So what have we done with these detectors? The only curve that I'm going to show is what is called the power spectral density curve in units of per root hertz as a function of frequency. All you need to just remember is, I plot a curve and I call it initial LIGO sensitivity. If a source is above that, I can detect it. The way I have worked out all the different curves, I have folded in all the data analysis that we can do. As a result, if you see a source, you will be able to, in above the curve, you should be able to see them. So that's the initial LIGO. We took about effectively 1 year of data with it. This is the advanced LIGO and Virgo plots. They are coming up soon, and that's the dream. That's the Einstein telescope. So let's look at the potential for observing different things. The first is our binary black hole guys. These can be seen, could have been seen up to 250 megaparsec, and nothing occurred in initial LIGO. But in the case of Einstein telescope, we will be able to observe binary black holes not just at redshift of 5, but redshift of 20. That is just one example. So the initial LIGO did not see anything, but what did it really do? The average reach of LIGO and Virgo for a 50-50 solar mass black hole was about 250 megaparsec, and for a 10-10 solar mass black hole, it was about a factor of 2.5 smaller, 100 megaparsec. So we could have observed those, that would have left a trace like that. That's a 10-10 solar mass black hole, no, 50-50 solar mass black hole. We didn't observe them, therefore we could set a limit on the rate at which these coalescences are occurring. For a 50-50 solar mass black hole, it's 0.08 per megaparsec cube, and for 10-10 solar mass black hole is 0.87. So the next would be binary neutron stars. We know they exist. We could have seen them up to a maximum distance of 50 megaparsec, average distance something like 20 megaparsec. With advanced LIGO, we will see them up to 450 megaparsec. With Einstein telescope, redshift of 2, 3, and you will notice something funny happening here. The frequency of merger, I stopped here somewhere, but it went down to lower frequency. And that is because when you put an object at a certain redshift, it appears heavier. And therefore, coalesces at a lower frequency. We saw that the loss table hour frequency goes like the inverse mass. So the redshift has considerable effect on these waveforms. LIGO did not see any of them. LIGO average reach for 1.35 was 16 megaparsec. You can read the other numbers. And LIGO Virgo best upper limits is then 130 per mega year per megaparsec cube. This is considerably larger than what we believe we will be able to see from the a few observed binary neutron stars. In addition to that, we can expect to detect neutron star black holes. Their reach might be 1.5 gigaparsec in advanced LIGO, 1 gigaparsec in advanced LIGO as opposed to 1.5 for binary black holes. What does it all mean? This summarizes what has been observed so far with initial and advanced LIGO and what we expect. So these lines here show you the rate upper limit we have already set. And these are the predictions. And the predictions are about an order of magnitude lower. But with advanced detectors, we improve the amplitude sensitivity by a factor of 10. We gain the rate by a factor of 10 to the 3. So in all these cases, we delve right into the heart of these predictions. But unfortunately, even if we don't observe, there are possibilities, 10 to the minus 8 per megaparsec cube per year. So we might not be able to make spectacular statements about the universe even if we don't observe, let's say after 1 year. After 10 years, we are going to reach those levels. So that's the time scale. Sorry. Sorry?
Are uncertainties in the different types of sources correlated in some sense? I mean, if you assume that in one it's much lower, would it?
The only one that we are really certain with any certainty is this, and that's 3 orders of magnitude. The other two come from, this has both observational uncertainty as well as the modeling, but these have only modeling. There's no observed thing, and it may artificially look somewhat smaller than that. They are correlated in the sense of being produced by these binary population synthesis models. I'm not even 20% through, but it doesn't matter. I think I'm going to just skip through some of these things very quickly. We can observe continuous waves. The Crab pulsar has, if it has ellipticity of even 1 part in 10 to the 6, you can imagine what a small ellipticity it is. It's less than a centimeter or so on a 10-kilometer radius star. So that's the kind of level of ellipticity we can detect. The generic predictions here, how far the amplitude is going to be, and so on. So I don't know why I thought my talk is 45 minutes. Okay, so
including questions.
okay, all right. So that's for the supernova. The expected supernova amplitudes at the level of 10 kiloparsec. These supernova, there are different models. They predict different amplitudes, and you can see them to different distances. Let me just summarize that's the summary of all the sources. You can see, and I had another 45-minute talk, and which I'm going to skip. Thank you very much.
Any questions for Satya?
It depends on the distance. I'll go back to that specific slide to answer that question. I mean, this is the binary neutron star, guys, right? It is true, if it is at 450 megaparsec, the merger will be outside. But you can push this curve, and instead of 450, if I make it 45 megaparsec, that's an order of magnitude higher, and therefore I will be able to see the merger.
The mixed binary, the next slide.
Oh, the next slide. Yeah, neutron star black hole? Yeah, okay. Yeah, it has to really occur close. I mean, these guys are orders of magnitude lower rate predicted. I can't artificially put it at 100 megaparsec. The rate will be very low. So if it is at 100 megaparsec, then I think we'll be able to see the merger.
Isn't that bad news to make the correlation with gamma ray bursts?
No, but that's neutron star black hole. We can see neutron star. I mean, even these, we can observe them. We don't observe the merger, but we observe them up to 1 gigaparsec. And if they are really progenitors, in fact, these have much better chance of producing a correlation between a gamma ray burst, because we can go up to 1 gigaparsec. Incidentally, there has been no gamma ray burst within the advanced LIGO horizon for all the period that we have observed gamma ray bursts. None. So the chance of finding a correlation is pretty low. And the only way to do that is via kilonova. And that was going to be my next topic. But anyway.
Any other questions? We still have like about a minute.
Well, what is the correlation?
So it takes, I don't know why, going forward always takes time. I don't know why. The correlation between gamma ray bursts and things like that? Is that what you're asking?
Well, then you said that you didn't have time to say it.
Oh, I will show just 3 slides of what we can do with gravitational waves. Maybe that's, it says fundamental physics, astrophysics, and cosmology, and I'll just show one example of each. So the most exciting thing that's coming along is the so-called multi-messenger astronomy. You observe events in gravitational waves, but you also observe transient events in various different detectors, and the idea is to cross-correlate them. The most beautiful example is that of a short gamma ray burst. Gamma ray bursts come in 2 varieties, the long ones and the short ones. And the short gamma ray bursts, which last for less than or equal to 2 seconds, are believed to be produced by short gamma ray bursts. And we have a question in the afternoon: what can we do if we don't observe anything for 5 years? And this is one thing we could do. If there is a gamma ray burst that occurs within our horizon and we don't observe it in gravitational waves, then that could be a big deal. And there are very interesting models that can be constrained by gravitational wave observations, and we can even produce triggers ahead of time so that it can be observed right at the time of merger. Those things is what I was going to say. So next, Let me just mention one thing about testing relativity. Maybe
While you're
the
finding that, Walter, if you're going to be talking next, you might want to come down here and get ready. You switched? Okay, John.
But Walter will give an entire talk.
Oh, that's correct. So, for instance, black holes are the most perfect macroscopic objects. They are characterized by only two things: their mass and spin. They also could have charge, but not astrophysical black holes. And you can measure the different quasi-normal modes and see whether it's a black hole or not. That's called testing the no-hay theorem. So let me then not skip all the details. Actually, if I go out of that and then come back, measuring the equation of state of neutron stars. I mean, we don't really know whether neutron star cores are made of confined quarks and quark gluon plasma, or like here free quarks, or if they are which kind of quarks and so on. So that's the neutron star equation of state question, and that can only be fixed, and there are many different equations of state, and that can only be fixed if you measure both mass and radius of a neutron star very accurately. And that's something that gravitational wave observations might be able to contribute, because we can measure the radius very accurately, although not the neutron star mass. So that's something. And finally, who is next? Please come here, otherwise I may not finish. And then cosmology with binary neutron stars. Okay, let me just finish that. You're waiting? Okay, please.
Okay.
How I left everything for you.